Thanks for joining. Welcome, everybody. Our own CITA National Fellow, Dr. Simon Blouin from the University of Victoria with us. Simon did his PhD at the Université de Montréal, graduating in 2019. He then worked as a postdoc at Los Alamos National Lab before moving this September to the University of Victoria, where he's a Banting Fellow in addition to being a CITA National Fellow. He's an expert on all things white dwarfs. And today in his talk, he's going to tell us about white dwarf evolution in the era of Gaia. So with that, I will turn it over to Simon. Go ahead, take it away.
Okay, thank you, Phil. So my research really focuses on developing the numerical tools that we need to use white dwarfs as accurate cosmic clocks. Initially, I've mostly focused on one aspect of this problem, which is to develop the atmosphere models that we need to measure the properties of white dwarfs to then infer their ages. But more recently, I've more focused on another aspect of this problem, which is to understand their interiors, and in particular, to understand how fast they cool down. So this is the work I want to talk about today. So this is work I've been doing over the last 2 years at Los Alamos National Lab. And it's mostly motivated by new observations from Gaia. So let's get started. So my plan for today basically is first to motivate why we care about white dwarf age dating. So why is it a useful technique and how is it relevant to other fields of modern astrophysics? Then from there, I will introduce a problem of white dwarf core crystallization, which is really a key piece of physics that we need to properly understand in order to model white dwarf cooling. And that's what I've been working on over the last 2 years. Then I will introduce the new observational puzzles that we have from Gaia that are challenging our understanding of white dwarf cooling and in particular of core crystallization. And from that, this will lead to the bulk of my talks. So I will discuss the theoretical work that I've done to try to reconcile the Gaia observations with our cooling models of white dwarfs. And finally, I will say a few words about what I'm planning to do next here at UVic as a CITA National Fellow. So please feel free to interrupt me at any time if you have questions. Okay, so start with the beginning. So how does a white dwarf look like? Well, 99% of the mass is located in a core, which is usually made of carbon and oxygen, but you can also have helium core or oxygen neon cores if you're at very low or high masses. This carbon-oxygen core is surrounded by a helium envelope of about 1% of the white dwarf's mass, and then you have a very thin layer of residual hydrogen. So the physical parameters encountered in white dwarfs, they span a wide range of conditions. So at the center, we have very high densities, very high temperatures. And in the atmosphere, we have gas to liquid-like densities with temperature from 10 to the 5 Kelvin for the very hot and young white dwarf, all the way to 3000 Kelvin for the oldest white dwarfs we know. So of course, what makes white dwarfs useful cosmic clocks is the fact that their evolution is very predictable compared to other stars. So because they've exhausted all their nuclear fuel, the only thing they can do for the rest of time is to simply cool down in this monotonic fashion. So the idea of white dwarf age dating is that if you can measure the temperature, mass, and atmospheric composition of a white dwarf, then you can infer its age, provided that we have accurate cooling models to relate those parameters to an actual cooling age for the white dwarf. So all those three parameters, we can obtain them quite easily by comparing model atmospheres of white dwarf to spectroscopic or photometric observations. And then we have our cooling tracks to transform that into an age. So that's a pretty old technique. It's been used for more than 30 years to measure the ages of different components of our galaxy, such as our galactic disk or globular clusters. But it's not because it is an old technique that everything that has to be done with this approach has been done. And in fact, today in this really big data era of stellar astrophysics, there are many new exciting applications that are becoming possible for white dwarf age dating. So I'm going to go through some of them just to give you a sense of why we should care about this technique, and in particular of why we should develop those accurate cooling models so that we can do this kind of work precisely. So a first application is that instead of just looking at the age of a stellar population, we can also reconstruct its stellar formation history. So basically, you look at the distribution of the ages of white dwarfs in a given stellar population, and from that, you can reconstruct the stellar formation rate. So this has been done recently using data from Gaia, and you can see here in particular, so you see the stellar formation rate as a function of how far away we look back in time. And there is this sharp peak here, which has been related to the merger of our galaxy with the satellite galaxy. So this is the kind of work that we're starting to be able to do with the large scale surveys that we have now. And obviously, to do this correctly, you need appropriate white dwarf cooling models to infer those ages. A second application has to do with exoplanetary science. So probably the most exciting advance in the field of white dwarfs during the last 10, 15 years has been the realization that about a third of those white dwarfs have recently accreted rocky debris from their own planetary systems. So the idea is that if you have a star in the main sequence with a planetary system, well, once the stars goes up the red giant branch and the asymptotic giant branch, it loses mass. And by losing mass, it destabilizes the orbits of its planets. And eventually, when you're on the white dwarf cooling track, well, those instabilities can scatter planetesimals, so things like comets, minor planets, or asteroids, toward the white dwarf. If they get really close to the white dwarf, they are torn apart by tidal forces and accreted onto the white dwarf surface. So we see the signature of this process in the spectra of those white dwarfs. So we see the presence of rock-forming elements in those white dwarfs. And then the idea is that by doing spectroscopy of those polluted white dwarfs, you can infer the chemical makeup of those exoplanetesimals. So that's pretty cool. And people are now comparing what we can infer from that to the composition of known solar system bodies. And you can infer many interesting things from that. So for example, in some cases, you can see that the signs that the planetesimal that was accreted was large enough to have undergone a differentiation process, so with the formation of a core and a mantle and that kind of thing. And as we're discovering more and more of those polluted white dwarfs, one thing that is becoming clear is that there are trends between the frequency of pollution of those objects, but also the composition of the accreted material as a function of how old the white dwarf is. And this is expected because if you form a planetary system 10 gigayears ago versus 3 gigayears ago, well, the chemical evolution of our galaxy is not at the same stage. So you're not starting from the same kind of nebula when you form your planetary system. So what we're able to do now is to look at trends with respect to the evolution of our galaxy, of how the composition of exoplanetary systems have changed through time. But again, for this kind of applications to be possible, we need to be able to measure white dwarf ages accurately. The third application, which is related to the last one, has to do with lithium. So we now have discovered a handful of polluted white dwarfs that show traces of lithium in their atmospheres. So the interpretation is that the accreted rocks, like the other polluted white dwarfs I presented, but that those rocks contain a sizable detectable amount of lithium. So this is interesting because it might help solve the cosmological lithium problem, which is a discrepancy between the lithium abundances measured in old stars compared to the lithium abundance predicted from Big Bang nucleosynthesis. So comparing the lithium abundances in old stars to that predicted by Big Bang nucleosynthesis is not easy because lithium is easily destroyed in stars. So it's not easy to relate what we measured in those old stars to Big Bang nucleosynthesis predictions. But here in white dwarfs, we have a whole new avenue to investigate this problem, because essentially what we're measuring is lithium abundances in rocks and not in stars. And so that isolate this problem of lithium being destroyed. That way we hope to be able to trace back the galactic lithium evolution and maybe help solve this cosmological lithium problem. So far we only have a handful of objects that are lithium polluted, but we are finding more and more of these. And if we have accurate age dating for those, for the old white dwarfs that show those lithium features, then we can really reconstruct the chemical evolution of our galaxy that way. Finally, a fourth application has to do with cosmology. So historically, if you go back in the 90s, for example, white dwarfs were really a competitive method to determine the age of the universe. But in recent years, they have taken more of a backseat because we have cosmological methods now that are much more accurate. But this may soon change because of the real data revolution that we have right now in stellar astrophysics. So in particular with Gaia, we have accurate distances to hundreds of thousands of white dwarfs. We're starting with Cosmology to be able to really probe the interior composition of white dwarfs. And of course, we have many upcoming large-scale spectroscopic surveys that will allow the chemical characterization of hundreds of thousands of white dwarfs. So with all this coming, it's the tide is slowly shifting, and white dwarf age dating may again become a competitive method to measure, well, to at least put constraints on the age of the universe. And this may become relevant in the context of the Hubble tension, which is this discrepancy between the Hubble constant as measured from distance ladder technique and as measured from cosmological methods. The idea here is that there are models that have been proposed to reconcile this discrepancy. So there's this early dark energy model. A key prediction of that model is that our universe would be slightly younger than the lambda CDM model. So the idea here is that if you find white dwarfs that are around 13 giga-year old, and that you know their ages very accurately, then we can possibly discriminate between those models. Okay, so that's what I had to say for why we should want to really develop accurate cooling models of white dwarfs. We want to use them as accurate cosmic clocks, and there's a broad range of different problems that white dwarf age dating can help solve. Now, a key problem with modeling the cooling of white dwarf stars is the problem of core crystallization. So the interior of white dwarf is of course, a very dense, completely ionized plasma. And in this plasma, the carbon and oxygen ions, they interact very strongly together, meaning that the plasma is highly coupled. As the white dwarf cools down, this coupled is only increased because you have less thermal energy. And at some point, it's so coupled that it just freezes into a lattice structure. So this is what we refer to as core crystallization. And it's a liquid to solid phase transition, meaning that it releases latent heat. And this latent heat release is suddenly a new source of energy for the white dwarf. It's excess energy that it has to get rid of in order to continue cooling down. And getting rid of this excess energy takes time, so it slows down the cooling of the white dwarf by about 1 giga-year. So obviously, it's an effect that's really important to take into account in our cooling models. But the release of latent heat is not the only thing that happens during core crystallization. So there's also a phase separation or fractionation process. So fractionation is usually, when we say fractionation, people usually think about chemistry, where, for example, if you heat up a mixture of two different liquids, well, the most volatile liquid will be favored in the vapor, and that way you can separate the two liquids. But this is also true, this kind of phenomenon is also true for phase transitions in general. So when you have phase transition between two different phases, if you have a mixture of different species, in general, the two phases won't have the same composition. So in the case of white dwarf, we have this happening from a liquid to a solid phase transition. And there are well-known down-to-earth applications of phase separation in liquid to solid phase transition. For example, ice beer, which is a really a strong beer, is made by putting a big barrel of beer outside in the winter, and then you just wait for ice to form, and you remove the ice, you throw it away, and the ice is poor in alcohol compared to the liquid, so that way you enrich the beer in alcohol. And it's something similar with ice wine, so they let the grapes freeze, and the solid crystals that are formed in the grape are preferentially enriched in water, and the sugar is pushed outside the water ice. So then when you press those frozen grapes, you just collect the sugar-rich liquid and you throw away the ice crystals, and that's what you use to make ice wine. So there's a very similar process going on in our white dwarfs. But here, instead of changing the concentration of alcohol or sugar, we are changing the concentration of oxygen. So the crystals that are formed in white dwarfs tend to be enriched in oxygen compared to the average liquid mixture. So because the white dwarf first freezes at its very center, where density is highest, this process essentially displaces oxygen ions from the outer layers of the core and towards the center. And moving those oxygen ions around is releasing gravitational energy in the white dwarf, which is a second source of excess energy with latent heat release that the white dwarf has to get rid of. So this also slows down its cooling. So we're talking about, once again, a slowdown of about 1 gigayear in white dwarf cooling times due to this phase separation process and the entering gravitational energy release. So very recently, thanks to Gaia, we finally identified the observational signature of core crystallization. And this allows us to compare our cooling models to what we see in Gaia data to check if the cooling delays that we think occur during crystallization actually match what we see in Gaia. So the reason why Gaia really changed the whole game is, of course, because it provided us distances to about 250,000 white dwarfs. And from those distances, well, you can lift the degeneracy between the radii and distances of white dwarf. And from that, you get absolute magnitudes. And also you get the masses of all those white dwarfs because the white dwarfs, they obey a very well-constrained mass radius relationship. So the plot on the left here shows the signature of core crystallization in Gaia data. So every dot you see here is one white dwarf, and they cool down from the top left to the bottom right along those blue cooling tracks. So you have 3 of them for 3 different white dwarf masses. So the one on the top is for a 0.6 solar mass white dwarf. So that's your typical white dwarf mass. And the 2 other ones are for slightly more massive white dwarfs. And the signature of core crystallization is this feature here that has been called the Q branch. So if you look closely here, there is an overdensity of white dwarfs compared to times before or after this Q branch. So if I follow this cooling track here, I see a certain density of white dwarf. Here I see an increased density, and then I see a lower density. And the interpretation is that the white dwarfs that are here, they are in the process of releasing their latent heat and their gravitational energy from oxygen phase separation, and therefore they slow down. Their evolution slows down, and that's why we see a pileup of objects in this region. It's really just a traffic jam of white dwarf. And it matches quite well with the theoretical expectations. So the orange lines here are showing the region where we think carbon-oxygen crystallization takes place. So that works fairly well. And you can also see this if you look at the luminosity function of white dwarfs. So that's another way to look at it. So this plot on the right is showing how many white dwarfs you have per different luminosity bins. So on the left, you have the hot young white dwarfs, and on the right, the old cool ones. And you see this, this increase here because at very high luminosities, those young white dwarfs evolve very slowly. So that's why we have less of them. But then the slope here is not continuous. We see this sharp bump here, which corresponds to the Q branch here. So that's the pileup due to crystallization. And finally, eventually, we have a drop-off here. And this drop-off is related to the age of our galactic disk. So in this sample of white dwarf, we don't have white dwarfs that are older, that had the time to evolve to lower luminosities. Okay, so that's cool. We can see for the first time core crystallization in astronomical data. So core crystallization was predicted to occur in white dwarfs back in the 60s, but arguably it's just 2 years ago that we finally got the direct observational evidence that it actually takes place. But if we look at this in more detail, and that's where the more interesting stuff is, it turns out that there's a big problem. So if you want to replicate those over densities of white dwarfs during crystallization, well, you need to assume that white dwarfs spend much more time than we think they should crystallizing. So it looks like there's a missing cooling delay. There's a missing energy somewhere in our model that we need to add in order to match this Q branch feature. So you can see this quite clearly on this plot on the left. So the top panel is showing the observed mass temperature distribution of a local Gaia white dwarf sample. And the two blue lines here, that's where crystallization takes place. So my white dwarf evolves at constant mass and decreasing temperature. When it crosses the first blue line, it starts to crystallize. And when it crosses the second one, it's done crystallizing and it's fully frozen. So we see that somewhere around the last 50% of the crystallization here, there's a sharp pileup in the data. We see an overdensity of white dwarfs. And when we try to replicate this using population synthesis simulations, we really don't see that, okay? And from that, we can infer that at this point of the white dwarf's evolution, there is a missing delay in our models of about 1 to 2 gigayears that we need to just artificially add to the models in order to be able to replicate this kind of feature. And there's an even worse problem if we look at the high mass end of the white dwarf mass distribution. So if you look at white dwarfs above 1.1 solar mass, there what we find is that there's a percentage of those white dwarfs that have to undergo an additional 8 gigayear delay in order to explain the observations. And that's so that's not just inferred from a pileup, but that's also inferred from the kinematic properties of those white dwarfs. So their kinematic properties are those of really old white dwarfs, but they are still at temperatures that are appropriate for young white dwarf. So it's from this discrepancy that you can infer this 8 gigayear delay. So those.
Before we move on, I have a question.
Yeah.
So you phrased the discrepancy in terms of time. So there's a discrepancy of 1 gigayear. What is this discrepancy in terms of energy per particle? How much energy per particle are we missing?
Oh, that's a good question. Well, it depends. It will depend on, okay. It depends a lot on when the crystallization takes place, right? Because so you can see that for different masses, I don't crystallize at the same temperature. So the high mass white dwarf, they are more dense, so they crystallize earlier. When you crystallize early, you have a very high, the white dwarf is still more luminous, And therefore, to have a given delay, you need to release more energy, because the delay will basically be the energy released divided by the luminosity of the white dwarf when that takes place. But I mean, so as for orders of magnitude, if I look at those white dwarf and I say 1 gigayear delay, that would be about 1 kBT per particle. Okay, so yeah, just because it's really of the order of 1 times the Boltzmann constant times the temperature of the gas.
Another quick question. On the previous slide on the color, the magnitude color plot, there's these 2 parallel tracks. Is that dA and dBs?
Oh yeah, okay. So here we see clearly a bifurcation, and yes, well, it's actually, yeah. So it's the hydrogen pure white dwarf and the. So at first people thought that's dA and dB, so pure hydrogen and pure helium. But if you look at the details, actually the pure helium and pure hydrogen, they go pretty much at the same place. And now the interpretation, well, we know that the second track here, so the top one is for dA, pure hydrogen, and the second one is helium dominated plus some pollution either from hydrogen or from heavy elements, such as the planet accreting white dwarf I've been discussing. Yeah.
Wait. Okay. So pure dBs are in the upper track, but then if you
I mean, if you plot pure dB, it's really close to pure dA on this plot. And I mean, we now think that pure dB is something that's I mean, they're really rare. Basically, you always have some pollution from something, because I mean, having no hydrogen at all is a bit challenging to create anyway. Because that would mean the white dwarf really destroyed. The star previously really burned all its hydrogen, and I mean, you always expect some leftovers.
And what's the composition of the Q branch?
Well, good question. So it was named the Q branch because initially people found that many white dwarfs in this Q branch have carbon polluted atmospheres. So about 50% of the Q branch have carbon polluted atmosphere, and that's much more than what we find in the white dwarf population in general. So that's the spectral type DQ. And DQ, so we know a lot of them at low temperatures, and there it's pretty well understood what happens is that you have a convection zone in the envelope that basically reaches into the carbon layers of the white dwarf really deep and brings back the carbon in the atmosphere. But having carbon polluted white dwarfs at higher temperature is not explained by this phenomenon. And the best explanation we have is that those white dwarfs are the product of mergers of 2 white dwarfs, and that, well, you can burn your hydrogen during that merger and you mix up everything. So that way you can explain why you have carbon coming up at the surface. And this also matches well with the fact that those are very high mass white dwarf. So, you know, around 1.1, 1.2 solar mass. So that's, of course, what you expect for mergers. But it's about half dA and half dQ in this Q branch.
Thanks.
If you, on this Q branch, you mentioned there was also a time discrepancy, but isn't that also understood if they're mergers?
So this has been, basically, you can explain a small part of the discrepancy, something like 1 gigayear, but you cannot explain the whole thing. It doesn't match. It just doesn't match.
Okay, thanks.
Okay, so obviously those gigayear large cooling delays, they're a big problem if we want to use white dwarf as accurate cosmic clocks. So we need to understand what's going on here. So that's what I've been working on. And the first part of this problem that I decided to work on is this carbon-oxygen phase separation, because that's really the most tricky part to model. So the latent heat release part is quite straightforward. but this phase separation it demands a bit more detailed physics models. So what we need to do to implement this process in white dwarf cooling models is to know the precise shape of the carbon-oxygen phase diagram. So the phase diagram tells us how much phase separation or fractionation there is between the solid and liquid phases. So this is a sketch version of the carbon-oxygen phase diagram. So on the left here, you have the temperature of the mixture, of the carbon-oxygen mixture, and the horizontal axis is the composition, so pure carbon on the left and pure oxygen on the right. So at first, the white dwarf is liquid, so it's still really hot, and it has some composition, and then it just cools down at this constant composition. And then you reach this line here. So this top line is called the liquid Zeus, and everything that's above it is always liquid. And this second line that we see here, the one below, is called the solid Zeus, and everything that's below it is always solid. So here what happens is that when you reach the liquid Zeus, that's where crystallization starts, and you form crystals that are enriched in oxygen by an amount that is given by the separation between the liquid Zeus and the solid Zeus. And now, because you form oxygen-enriched solids, it means that you've depleted the liquid in oxygen. So you start moving to the left along this liquid Zeus line. And this just happens over and over again. So you deplete the liquid in oxygen until you reach this point in the phase diagram, which is known as the azeotrope. And when you reach the azeotrope, there is no more phase separation that can take place. So the rest of the crystallization process will simply occur at constant composition. So you can see from this that it's really important to know exactly where this point is because it tells us when this process stops. And we also precisely need to know the separation between the liquid Zeus and the solid Zeus. So we were not entirely satisfied with the techniques that have been used in the past to compute this carbon-oxygen phase diagram. So the first option that's been used is based on analytical free energy models, where you build a free energy model for your carbon-oxygen mixture using a linear mixing rule. So where you take the free energy of a one-component plasma for the carbon plus the free energy of the one component plasma for the oxygen, and from that you compute the phase diagrams. So a big issue with those with this approach is that the free energy models that people use, they are fitted to simulation data, but depending on the functional form that is assumed, you can end up with different shapes for your phase diagram in the end. And even though those choices that you made for the functional form is completely arbitrary. And that's just because those calculations are extremely sensitive to small details. So ideally, you don't want to rely on separate simulation data and perform interpolation in that. Instead, you want to really perform the calculations at the parameters in which you're interested so that there is no artifacts like this that are introduced. So one approach that solved this problem is the two-phase molecular dynamics approach. So basically, you take a bunch of carbon-oxygen ions, you put them in a big box, you place them in a solid configuration on one side and in a liquid configuration on the other side, and then you let the system evolve according to Newton's laws of motions, and the ions will diffuse sometime from one side of the interface to the other. And after some time, there is an equilibrium that is reached. And then you can just read off what's the oxygen concentration in my solid and in my liquid. And this gives you 2 points on your phase diagram. So that's a pretty cool technique. But the problem is that you need to perform extremely large simulations for this to work properly. And this becomes so costly that you can only partially sample the phase diagram. And that's not great for applications to white dwarfs. And in particular, it's because it cannot properly resolve the position of the azeotrope point. that this approach is not really suitable. It's also sensitive to finite size effects. So there's this interface here that is breaking the symmetry of the system, and this is introducing artifacts in the calculations that are not super easy to get rid of. So because of those limitations, we designed a new approach to compute the carbon-oxygen phase diagram that would be free of those problems. So we've developed what we call the Clapeyron integration technique. So it's based on an approach that has been used in the past for neutral mixtures, but we adapted this approach here for electron-ion plasmas. So I won't go into details, but the basic idea here is that we integrate the Clapeyron equation. So the Clapeyron equation is this thing that gives you, so under its simplest form for a one-component system, it gives you the slope dp dt of the coexistence line between two coexisting phases. So here what we do is that we develop a generalized version of the Clapeyron equation for our multi-component system, and we just integrate this equation to map the whole phase diagram. In order to evaluate our generalized Clapeyron equation, we perform Monte Carlo simulations of the plasma mixture to obtain the quantities that we need to perform this integration. So it works really well, and we've obtained this really nice detailed version of the carbon-oxygen phase diagram. So here is shown in red, and I'm comparing it to what's been previously found using molecular dynamics techniques. So you can see that we have a really good resolution of the azeotrope point, which is critical for white dwarfs because that's where phase separation stops. And we also have a more high resolution picture of the amplitude of the fractionation process for different oxygen abundances. Another thing that I'd like to point out is that this approach is hundreds of times more efficient from a computational point of view. So that's not critical for this problem. I mean, 1 million core hours is not that much of a big deal nowadays, but it will become really important in the next few slides, because here that's the phase diagram just for the carbon-oxygen plasma. But later on, I will talk about the 3-component carbon, oxygen, and neon phase diagram. And in that case, you need to integrate the phase diagram along an additional dimension. So our approach can easily scale to that kind of problem, whereas the molecular dynamics approach really can't scale to an additional dimension. Okay, so we have now a really good picture of carbon-oxygen phase separation, but obviously the kind of changes that we see here are not really big. So it's leading to differences in cooling times of just a few hundred of million years. But that's not the kind of giga-year large changes that we were looking for. So we need to look elsewhere at what could be the piece of missing physics that could explain those missing cooling days. So the next key suspect is neon-22. So neon-22 is a trace species in white dwarfs. So for a typical carbon-oxygen white dwarf, it should make up about 1 to 3% of the white dwarf's mass. And how much neon you have exactly depends largely on the metallicity of the progenitor of the white dwarf. So this neon-22 is there because during the CNO cycle, this step here is the slowest. So you end up with a bunch of nitrogen-14 at the end of the hydrogen burning phase. And later on, during the helium burning phase of the star, you can convert this nitrogen-14 to neon-22. So neon-22 is a prime suspect because of its 2 excess neutrons. So it has 12 neutrons and 10 protons. And this makes it very different from carbon-12 and oxygen-16 because it changes its mass to charge ratio. And because it has a different mass to charge ratio, it means that if you take 1 gram of neon-22 from the outer layers of your white dwarf and you bring it to the center of the white dwarf, you will release 25 times more gravitational energy than if you do the same thing with oxygen-16. So even though it's just a tree species, it has the potential of drastically altering the cooling of the white dwarf. Then the question is, well, how do you bring this this neon-22 from the outer layers to the center. So a well-known way of doing that is simple gravitational settling. So there's a net downward force acting on the neon-22 ions because of their higher mass to charge ratio. And because of that, the neon will sink towards the center of the white dwarf. But a key aspect of this process, that's shown here, if I pause it, the key aspect of this process is that it can only take place in the liquid layers of the white dwarf. So once the white dwarf freezes, and that's what this animation is showing, the neon-22 gravitational settling is stopped because the neon-22 can no longer sink once it hits solid layers in the white dwarf's core. So that sets an upper boundary on the kind of delays that you can get, which are well below 1 gigayear. And also, perhaps more importantly, it means that it cannot be the process we're looking for, because we're looking for a process that is releasing energy when the white dwarf is crystallizing, whereas this process is inhibited by crystallization. So that's not really what we're looking for. But still, the neon-22 that's in the white dwarf, if you compute the gravitational potential energy that it has, it's plenty enough to produce a multi-gigayear cooling delay. So this energy is there, and it's just a matter of finding a way to release it by bringing the neon to the center of the white dwarf. So gravitational settling can't do that because it's inhibited by the freezing of the white dwarf. But perhaps there's another way. So we think we found this other way of bringing the neon-22 to the center of the white dwarf. And this other way has to do with phase separation. So we took our Clapeyron technique, which we've compared to previous calculation, and it works really well for the carbon oxygen case. And now we've applied it to the slightly harder problem of the 3-component carbon oxygen neon mixture. So it's not easy to visualize how a 3-component phase diagram looks like, but the upshot of our calculations is that we find that under a wide range of different parameters, the solid crystals will tend to be impoverished in neon compared to the liquid mixture. So that's what this plot here is showing. And if you have less neon-22 in the crystals than in the liquid, it means in turn that the solid phase will be lighter than the liquid. And that's something completely different from what we're used to. So we're used to solids that are heavier than the liquid, so they just stay where they're formed. Whereas here we are predicting that the crystals, the neon-22 depleted crystals, will want to float in the white dwarf once they're formed. And this, we think, will lead to this process that we call neon-22 distillation. So the idea is that you form those crystals that want to float in the white dwarf, so they float up. By floating up, they displace liquid that is by definition enriched in neon-22 because the crystal is itself depleted in neon-22. Eventually, this crystal melts, mixes with the liquid, and this process just keeps going. So you keep pushing crystals up and then pushing neon-22 rich liquid down until you reach a critical quantity at a critical composition at the center of the white dwarf, which is the azeotrope point of our 3-component phase diagram. And this critical quantity is 20% neon. So when you reach 20% neon, then the white dwarf can freeze at a constant composition, and this distillation process stops. But 20% neon is a lot compared to the 2% neon or so we have in the core in general. So this means that this process can take basically all the neon that we have in the core and concentrate it in a tiny neon-22 rich central core. So that's exactly the process. This process has exactly the right characteristics that we want to explain the missing cooling delays, because 1, it's releasing a lot of gravitational energy, and 2, it happens exactly when the white dwarf is crystallizing. And we know from Gaia data that the missing cooling delay is exactly when white dwarfs are in the process of crystallizing. So this another key aspect of this process is that it's very selective. So depending on the composition of your white dwarf, you will or will not have this process taking place. So that's this plot here is a summary of what we find with our three-component phase diagram calculations. So what it's showing is that depending on your composition, so on the top you have the oxygen mass fraction, and on the right you have the neon mass fraction. So if you're in this blue region, then you can have distillation. So the solids are lighter than the liquid and they float. Whereas if you're in the orange region, the solids remain heavier than the liquid and you don't have distillation. So let's say you have 60% oxygen in your white dwarf. Then if you have a more than 2% neon abundance in your white dwarf, this process will kick in right when the white dwarf starts to crystallize, and you will form this neon-22 rich core. If you have less than 2% neon, so for example, for a solar metallicity progenitor, we predict 1.4% neon in white dwarfs. Well, in that case, at first, the white dwarf just crystallizes as normal, so there's no distillation. But as carbon-oxygen phase separation takes place and the crystallization front moves outward, you have less and less oxygen in the liquid phase because you're pushing it at the center of your white dwarf. And therefore, you're moving to the right along this arrow here towards decreasing oxygen concentration. And at some point, you will cross this boundary and you will trigger the distillation process. And it will be the same thing as in this previous case, except that here, instead of forming a neon-22 rich transfer core, you'll be forming a neon-22 rich shell at some radius outward in the white dwarf. So this will release a lot of gravitational energy too, but obviously much less than forming this neon-22 rich core. So my hypothesis is that those
5-minute warning, just 5-minute warning.
Thanks. Is that those two different outcomes, they correspond to the two missing cooling delays that we've identified thanks to Gaia. So this, if we compute the energy released by this process, assuming a slightly enriched 3-4% neon abundance, we find cooling delays of the order of 8 gigayears. So exactly what we need to explain this ultramassive cooling anomaly. So the interpretation here would be that this the white dwarfs that are delayed by 8 gigayears among the ultramassive white dwarfs would be white dwarfs that are slightly enriched in neon compared to standard white dwarfs, and this can be achieved, for example, if those stars were formed in alpha-rich environments or things like that. And then the second cooling delay, well, that we see for all the other white dwarfs, it would be related to the formation of this neon-22 rich shell. And again, if we compute the cooling delays that we get by forming the shell from the gravitational energy that's released by that, we find 1 to 2 gigayears. So it matches with the cooling delay that we need. And the morphology here of the pileup is also consistent because we see that this pileup happens mostly towards the end of the crystallization, not at the beginning. And here the shell would be formed later during the crystallization. So that matches really well. So we still have to implement this process self-consistently in white dwarf cooling models to do population synthesis and directly compare to the observations. But I think that this one process alone can go a long way into solving those problems.
Quick question.
Yeah.
Before you leave this, so this is a very nice idea, but my understanding of what white dwarf structure is emerging from stellar evolution calculations is that as you extend from about 1 solar mass to 1.3 solar masses, the range that seems to be, indicated here. There's a much more complicated picture of the transition from CO to oxygen, neon, magnesium dwarfs, and that you may in fact have dwarfs that have some hybrid composition. Or I guess my essential question is, don't you expect to have see a much wider range of neon abundance in the white dwarf?
Okay, yeah, good question.
Mass range than you're assuming.
So in oxygen neon white dwarfs at high mass, it's neon 20 that you have, not neon 22. So even in oxygen neon white dwarf, the neon 22 abundance that you have is of the order of a few percent, just as in carbon oxygen white dwarf. But then there's a separate question here that I get from your question, which is can we really assume that those high mass white dwarf have carbon oxygen core and not oxygen neon core? There are ways to produce oxygen neon, carbon oxygen white dwarf even at high masses. I mean, it's really an area of active research, and it's still not clear which fraction of those white dwarfs are carbon oxygen versus oxygen neon. But in any case, the neon 22 abundance is always predicted to be really small.
Okay. Thank you.
Okay, so just to finish quickly, so the what you can then ask me as well is, does it make sense to assume, for example, 60% oxygen in the white dwarf core? So everything I've described, really, you can see that it's sensitive on how much oxygen you assume there is in the white dwarf. And it turns out that's not a well constrained quantity. So the oxygen concentration in white dwarf is still really unclear, and that's mostly because of uncertainties related to the treatment of convective boundary mixing in the 1D stellar evolution codes that we use to produce our white dwarfs. So there is the formation of the semi-convective interface during the core helium burning phase. And it's really unclear how to treat mixing in this region. So different codes use different prescriptions, and that leads to different predictions as to how much oxygen you actually have in your white dwarf. And obviously, changing the oxygen here between 70% and 50% is making a really huge difference for this process of distillation. So that's why I'm excited to now work in Fox-Orbit group at UVic. So we have access to this ppm star code, which will allow us to perform the first full sphere high resolution 3D simulation of the helium core burning phase. So we can actually see how much mixing there is in those stars, and then correct the 1D stellar evolution models accordingly, and then hopefully obtain more accurate predictions for the carbon to oxygen ratio in those white dwarfs. Now is a really good time to do this kind of research because we have many constraints coming from astrocosmology. So on one side, we have astrocosmology from the core helium burning stars, where people are able to constrain the extent of the convective core, so we can compare that to our 3D hydro calculations. And on the other end, we are starting to have constraints from astrosysmology of white dwarfs themselves, where you can really do a cartography of the interior chemical profile. So with those two observational windows and our 3D simulations, we hope to be able to make significant progress on this issue and ultimately make white dwarfs more accurate cosmic clocks. So I guess I will just leave my summary here and take any question you may have.
Thanks very much, Simon. Very interesting talk. Already during the talk, but there's time to open it up for any others. Does anybody in the room or on Zoom have a question?
On your last point, to what extent is the carbon plus alpha to oxygen reaction still a large uncertainty?
Good question. So it is still a significant uncertainty, but the mixing really dominates. So I think the numbers, so if I go back here, so for the location of this plateau that we see here, I think from the nuclear burning reaction rate, it's a plus or minus 0.03 or 0.04 uncertainty. But for the mixing, it's more like 0.010. So, yeah.
Okay, thanks.
Any other questions?
Well, a slightly disjoint question. So as you follow the massive white dwarfs observationally beyond this pileup, how well constrained is their abundance as a function of age?
You mean the core composition, or
just the once you get to ages of several gigayears,
Yes.
are we tracking accurately now what the abundance of the massive white dwarfs is, or is the statistics starting to become poor once you get above an age of several gigayears or so?
Well, so if we talk about the atmospheric composition, which is the only thing we can directly observe, when you get to really old white dwarfs, the problem that we have is that below 5,000 Kelvin, you no longer have hydrogen lines or helium lines in the spectrum. So you end up with a flat spectrum. And in that case, it's really hard to discriminate between helium white dwarfs and hydrogen atmosphere white dwarfs. The only way you can discriminate between the two is when those white dwarfs are actually accreting rocky debris, because then you can see from the shape of the lines whether it's more consistent with hydrogen rich or helium rich. But yeah, I guess to answer your question, it's pretty well constrained all the way to the oldest one, except at really low temperatures where it's hard to tell.
Yeah, actually, what I meant was not so much the surface composition as just the volume density of white dwarfs in the galaxy.
The volume density.
So you're seeing.
Oh yeah, okay. When I showed
an overabundance at a certain age in this pileup zone.
Yeah,
but
let me go
beyond
back
that,
to this. Okay, I will share. Sorry, nothing else. Okay, so yeah, okay, yeah. So this thing here is basically what you're talking about. So that's the volume density of white dwarf as a function of their luminosity.
Yeah.
Well, the cutoff that we see here for those massive white dwarf, that's before the Gaia observational cutoff. So we know that this cutoff is real, and that's just because those white dwarfs, they did not yet have time to evolve to lower luminosities. And there is also this, that's one explanation. That's one part of the explanation. And the other part of the explanation, which you can kind of see from the observations, but it's a bit hard, is that once they are crystallized, they cool down really fast. So you enter in a kind of quantum regime where the heat capacity of the white dwarf decreases really rapidly, and then the white dwarf can cool down very rapidly. So it's a combination of those two things that is giving us this. But we know this sharp drop off, but we know that it's not observational.
Question? Considered the effect of the neon in the core. Maybe a naive question, but why neon? Is there, what is the next most important element for that kind of mechanism, and is it significant at all, or is the correction just negligible?
Yeah, well, then the next most abundant species, you have to go to like iron 56, and then you're talking about 20 times. It's like 0.1%. So people have really recently done calculations for that, and the delays that you get are extremely small compared to what we have here. So we don't expect. And we also looked, so in oxygen neon white dwarf, then you have more species. You also have a bit of magnesium and sodium, and we did those calculations too, and found that essentially nothing important happens there. So this process is really just for neon 22 in carbon oxygen white dwarfs.
Okay, we're at the top of the hour, so let's all thank Simon again. And Simon, if you can stick around on the Zoom, anyone who wants to chat with you, we'll keep the connection open. So thanks again.